response of unsteady aerodynamics as small angular using potential flow. So he got this complex transfer function, magnitude and phase. Okay? And this is what we're gonna frequency response. So in the last lecture, it was a review. So I did most of the derivations, but sometimes I skip a few steps in the middle. But now when we are deep into unsteady aero, I will not skip anything. We will do Tedorson in detail. Okay? And it's very hard to find it combined in one book. I mean, you can mix and match from books and make your own story. So we will do it in detail. We'll do it step by step. Derive Tedorson. So it will take the rest of this lecture and maybe the entire coming lecture, maybe some of the next one, but we'll get there. So Tedorson and Wagner, so like I said, remember this name because Wagner developed what? What's this? What is this response from a dynamical system point of view? What's this response? What's this kind of curve? You see it? Step response. So Wagner determined the step response of the lift. Okay? Tedorson developed the frequency response of the lift. But it has much more physics, actually, his derivation. So we will do his derivation in detail and then touch upon Wagner. So to do Tedorson, let's recall our tools. What do we have? What do we have? So we are potential flow, right? So na plus square phi equals 0, na plus square left psi equals 0, na plus square f equals 0 complex potential, right? So this is, we have at our disposal. We also, with 2 dimensions, potential flow, so together means that we can do conformal mapping. So in particular, since we're doing a flat plate, in particular, we have a map from here to there. It's zeta plus a squared over zeta, right? If this is the radius, then this is 2a, negative 2a, okay? And what else? Can you tell me what else? We have this equation. This is a PDE. Any differential equation is subject to what? Subject to what? You cannot solve. I cannot tell you solve this PDE. I mean, it doesn't make any sense. I have to give you what? What? Boundary conditions. Exactly. So what boundary condition do we have? We just played with it a little bit in the last lecture. The no penetration boundary condition, right? Do you have something more? Anything? We're trying to get all the tools. So in our disposal, it's a hard problem to determine the frequency response, and actually Tedorson was very lucky. And brilliant as well, for sure. So we need to know what we have at our disposal. We have no penetration boundary condition, because I cannot solve this subject to no boundary conditions. What else? What else? What else we essentially need? Or we essentially at least needed and used in steady aerodynamics? Because potential flow does not generate lift. What did we use? Come on. What did we use?
Gamma.
Okay, I mean it has to do with gamma, so we need tools. It's the contact condition tools, right? And also the conservation of circulation. We will consider in detail several aerodynamic models, the derivation of several aerodynamic models, Tedorson and others. And you will see that they all rely on this triplet. It's just with different orders and different spirit. But if you have these and apply them the right way, you can do whatever you like, okay? Whether it's correct or not, but you will develop an aerodynamic model. Whether it's accurate or not, I'm sorry. I mean, it will be physically correct, but whether it's accurate or not, it's something different. By this framework, we usually get what? We get at least phi. We solve the PDE. We get phi, the velocity potential, or F, the complex potential, so which means that we get the velocity field because it's simply the gradient of this guy. But how we get the pressure? If you have velocity, how to get the pressure? How we get pressure? Come on, guys. If you have velocity, how to get pressure? Bernoulli, right?
As erasing, right?
Exactly, and we are. But it's more than that. The Bernoulli that you know in undergrad is the steady version. We have an unsteady version. We're going to derive it right now. So this framework plus the unsteady Bernoulli completes everything. Okay. So let's derive the unsteady Bernoulli just to have it in our disposal. So we are. Oh, come on. So we are potential flow, meaning incompressible irrotational. Okay. So here's the governing equation: rho du by dt equals negative nabla b, and I don't need to assume inviscid. Why? Because the viscous shear stress goes away. We already showed that before. The other term goes away because of incompressible irrotational. Okay, so if you remember, this is the total derivative, so this is partial u partial t plus u dot nabla u. And we'll have here an identity, nabla u dot u, so this is actually u squared, is what? Twice u dot nabla u plus twice u cross nabla cross u. Very easy relation. But this is what? This is what? Exactly. This is 0 because it's irrotational flow. Okay? So this guy, the very bad term in the Navier-Stokes equations, now you get it as the gradient of a scalar u squared. So I'll replace this here as the gradient of u squared. So I have rho, maybe I'll divide by rho, so partial u partial t plus the gradient of u squared equals negative nabla p divided by rho, because it's incompressible, I can move rho around. And remember, because it's potential flow, this guy is nabla phi, right? So you have nablas all around. Nabla here, there, here. So let's take nabla as a common factor. So I have nabla acting on p over rho plus, or let's do it with this order. So partial phi partial t plus u squared plus p over rho is constant, right? Is 0, I'm sorry. Any question? Any question? Okay. So this is derivative with respect to the space is 0. So this means that this thing doesn't change with the space. It's constant everywhere. So p plus 1/2 rho u squared plus rho partial phi partial t is constant with respect to space. So it might be function of time. This is the unsteady Bernoulli. Okay. I mean, the version that you know in undergrad, p plus rho u squared equal constant. If it's unsteady, you need to add the acceleration term here. Okay? So we're developing a linear theory, so I'm going to linearize this because I don't like the u squared. So we have p infinity and u infinity to get the constant at the right hand side. And linearize about u infinity in the sense that your u is u infinity plus little u in the I direction plus little v in the j direction. So u squared minus u infinity squared is simply 2 u infinity u, is approximate. So our linearized unsteady Bernoulli is b minus b infinity is equal to minus rho u infinity u, which is partial phi partial x, plus partial phi partial t. This is the linearized unsteady Bernoulli. We will use it over and over again. Tudorson in particular used it. Okay? Any question? So let's, since we derived it, let's get the lift out of it. What's the lift? So the lift is the integral so if we have our, this is what Tudorson considered.